Good morning, everyone. My name is Juan Manuel Restrepo, and I will be presenting my work on superstructure optimization for the design of ethanol upgrading processes to distillate range fuels. This work has been done under the guidance of Professor Crystal Maravillas now at Princeton University. Now, I want to start by posing one question. Why do we want to upgrade ethanol? And there are fundamentally three things that I want to say about this. The first one is related with the ethanol blending wall. Now, technically, we know that ethanol can be blended at a higher level than 10%. But we know also that there is legislation in place that limits the amount of ethanol that can be added into gasoline in the United States at least to 10%. This basically limits the amount of ethanol that we can produce in total. And we can see from the plot that from 2015, the demand and the supply are actually the same. This basically means that if we start increasing the amount of ethanol that we produce, there might be some scenarios in which we're going to have a surplus of ethanol in the market. There is a second reason for which we would like to upgrade ethanol, and is the current fuel demand trends. You can see that the projected gasoline demand is expected to decrease. The penetration of electric vehicles, the increase in efficiency, might lead to a reduction in the gasoline demand. This is in contrast with the demand of other middle distillates like diesel fuel. Now, since ethanol is blended with gasoline mainly, then what we can expect again is a decrease in the ethanol demand. Finally, there is a third reason. We know that ethanol as a fuel can be blended with gasoline, and it's in general a good blend for that one. However, when we consider other fuels of interest like diesel or jet fuel, the compatibility between ethanol and those fuels is not so great. Let's consider an example, the flash point over here. You can see that ethanol has a flash point close to 13 Celsius, while the minimum required for diesel is 15. So the bottom line that I want to stress is that there might be a surplus of ethanol, that is likely, and second one, that ethanol has important limitations as a fuel. Now, these realities have motivated researchers around the world to find different strategies to transform ethanol into other set of molecules with different properties. Now, this plot over here shows the different chemistries that can be used to transform ethanol into different energetic products of interest like jet fuel or diesel. At a high level, what we can say is that ethanol can undergo first a transformation into higher alcohols by means of a Gerbeet coupling reaction, which are then further transformed to produce jet fuel and diesel. Or alternative, it can be transformed into olefins, like in the bottom part of the plot. And then these olefins can be oligomerized to produce jet fuel and diesel. But more than the specific chemistries that can be used, what I want that you perceive from the plot is that there is a wide variety of chemistries that can be used for the transformation of ethanol into different fuels. And with those chemistries, there is also a wide variety of catalysts that can be used. And this basically is at the same time an opportunity because we have a wide range of molecules that we can reach, and we can actually exploit that chemistry to produce the fuels that we're interested in. But it's at the same time a challenge, because if we're interested in finding a specific optimal strategy to transform ethanol into something that we're interested in, and we want to explore this systematically, it's going to be very difficult. There is many options, and we need to design a strategies that allows us to survey all those alternatives simultaneously. I want to discuss one specific example that is focused on introducing the point that we want to make. How do we design this upgrading strategy? Now, when I mention an upgrading strategy, I basically mean the sequence of chemical transformation that leads to the production of a fuel with tailored properties. One example is presented here. We have ethanol that is dehydrated to ethylene, and then ethylene is oligomerized, and then we obtain a jet fuel, basically. Now, there are three elements that I want to highlight within this specific strategy. The first one is the molecules that will undergo a specific transformation, ethanol, which is dehydrated, and ethylene, which is oligomerized. The second one is that there is a set of chemistries that are used for the transformation of these molecules. We see that ethanol is dehydrated in a dehydration reaction, and ethylene is oligomerized. Now, finally, there are the specific processes that allows us to realize these chemistries. You can see that dehydration is performed by means of a single catalyst, while the oligomerization is performed by means of a nickel-based catalyst. Then the question is, when we have a significantly high number of both chemistries and catalysts, how are we going to survey and select the specific upgrading strategy that will produce the fuel that we want? And we want to add one complication. You mentioned that you noticed that I mentioned that the fuel that we want, and this basically means that I don't want to be constrained by the specific properties of fuels currently available. I want to be able to design strategies in which the properties of the fuel that we obtain are actually decided by me, and that such that they can be better than the fuels currently available. And in order to do that, what we can do is, well, let's first formulate the problem in the following way. We have a set of chemical components that can be transformed, a set of technologies for the transformation of these components, a set of processes available, and now we know the capital and operating cost associated, and a set of products with specified properties. And what we want is to find the optimal strategy that allows us to produce the fuels with tailored properties that we want to produce, while considering systematically these three levels of decisions that I have mentioned. That is the molecules that will be transformed, the chemistries associated, and the processes that will realize those chemistries. Now, in the process and systems engineering community, a common strategy that can be used to formulate this problem is by means of a superstructure optimization. Now, superstructure can be understood as a network in which all the decisions of interest are embedded. And what we have done is to design a superstructure architecture in which we have embedded all these levels of decision. This architecture is represented on the left, and it contains three levels. At the bottom, you see what is known as a module, and this basically is associated with the specific processes that will be used to realize a specific transformation. In the previous example, it would be the Sendol catalyst that is used in example for the dehydration of ethanol into ethylene, or the nickel-based catalyst that is associated with the oligomerization of ethylene. Then we can group together all the different modules that are used for a specific chemical transformation. And what we get is the second level, which is known as a technology or a chemistry. Now, all the technologies that can be used for the transformation of a specific chemical component are grouped together in a technology group. In this case, we can think, in example, in the case of ethanol, we can dehydrate it, as I mentioned, to ethylene, but there are other alternatives. We can transform it by means of Gerber coupling or by condensation. All of them will be in the technology group. Now, when we see the technology map or the technology superstructure for ethanol, what we obtain is something like what is presented in this part of the plot. You can see that ethanol, which is here on the left, can enter the superstructure. And there is a number of different alternatives for the transformation of ethanol. You can see that the dehydration of ethanol will produce ethylene. And then we have a number of alternatives. Ethylene can be oligomerized. And after the oligomerization of ethylene, other molecules produced can undergo further oligomerization. Then the question is, how do we determine the optimal sequence that maximizes our profit associated with this specific superstructure? And what we do is to formulate a mathematical problem that contains mass balances, capital and operating cost estimations, some logical constraints that enforce the connectivity within the superstructure, and a fuel property model. And we formulate this one as an optimization problem. Now, this specifically allows us to explore a number of questions of interest. Like, an example, what is the optimal biorefinery that will produce a specific fuel like gasoline or jet fuel or diesel, or a biorefinery that produces a multi-product blend of fuels? And the results that we obtain are very interesting. Let's consider an example, a multi-product biorefinery that produces diesel and gasoline. You can see that we have a feedstock of ethanol, and our framework have found the optimal strategy, which in this case consists in the transformation by means of Gerber coupling of ethanol into higher alcohols, and then the further transformation into ethers and the dehydration of part of the hexanol for the production of the diesel and the gasoline. Now, the framework has embedded an economic estimation, and we can explore how that goes. You can see that in example, this is the capital cost, operating cost, excluding feedstock, and the cost of the feedstock. And you can see that the major driver of the cost is the feedstock cost. So you can start thinking in strategies to improve the cost based on this cost distribution. You can further see that in terms of both the capital and the operating cost, the lion's share of them corresponds to the first chemistry associated with this system. In this specific case, it would be the Gerber coupling chemistry. So you would like to design a very efficient Gerber coupling module to improve the economics of the system. And additionally, we have estimated the fuel properties. So you can see that the properties of the fuels that we are producing satisfy the requirement that we have, and that the composition of these fuels have been tailored such that these properties are satisfied. And we can replicate these results with other fuels, like in example with diesel fuel. In this case, the optimal strategy that we obtained consists again in a Gerber coupling reaction, but instead of having just one dehydration, what we have is a sequence over here of oligomerization reactions, a strategy that has been actually suggested in the literature, and it's interesting that our framework is able to find it. And we can explore again the economics of the system, which with similar conclusions to what we have, and the fuel properties associated. But the bottom line is that the selection of these processes, the connections and the fuel composition, those are non-intuitive for the engineer. And only the systematic formulation of the problem has allowed us to find the specific solutions associated with this system. Now, a second question that we might be interested in exploring is, what is the interplay between the properties and the composition? And in the case of diesel fuel, we're interested in exploring what happens when the cetane number changes. Now, high cetane number is generally associated with the possibility of operating engines more efficiently, specifically in the production of NOx emissions. And it has been suggested that high cetane number can really have a strong impact in the reduction of NOx emissions. In the US, the current mandate says that cetane number must be at least 40. In Europe is 50. And what we want to know is what happens in terms of process and economics when we start to produce better fuels. And you can see that there is a significant change in these biorefineries. When the cetane number is 40, what we have is this biorefinery already described, in which higher alcohols are produced by Gerber coupling, dehydrated, and then oligomerized to produce a diesel blend. But when we start to have a requirement of higher cetane number, what we see is that the etherification module, which is over here, start to increase, which is physically very intuitive because ethers have very high cetane number and have been suggested to as diesel additives. So there is a relation between the process that we obtain and the fuel properties that we have. And that, of course, have an impact both on the economics of the process. You can see that the profit, in example here, decreases when the cetane number increases, and the composition changes. Here, the ether fraction represented by these yellow squares is absent. And when we start to increase the cetane number required, the fraction of the ethers significantly increases. So we can see that there is a trade-off between the fuel properties and the profit, and that once the property becomes binding, the profit, the fuel composition, and the processes are modified as a function of the fuel specification. Now, with this, I want to conclude by saying that we have developed a framework for the design of ethanol upgrading biorefineries, simultaneously considering 3 levels of decision: which substrates and intermediate products should be processed in the biorefinery, which technologies should be used to transform them, and what specific processes will realize these technologies. And we have studied the relation between fuel properties, process synthesis, and economics, showing that process and fuel composition are adjusted when the constraints on the fuel properties are tighter, and that the economics of the process are a function of the fuel property constraints. We believe that the understanding and exploiting of these interdependencies is fundamental in the development of processes for the production of fuels with superior properties. Now, these are some references associated with our work, and I'll be happy to take any questions. Thank you very much.